Hi again, Dick Trudgeon again from the CW Math Department, and we're going to talk a little bit today about the algebra of vectors. We looked a lot the other day at the vectors themselves. This morning we're going to take a look at the algebra of the vectors and working with them algebraically. So let's get started there with the forms that a vector might take. The first form a vector might take is the component form. When you think vector 2, 3, you know, it can be confusing because some people look at it and think, oh, well, I thought that was a point 2, 3. But that isn't a point 2, 3. It doesn't even necessarily go through point 2, 3. It means it is a vector that has an x component of 2 and a y component of 3. Now, usually they'll put the little vector signs on that so you know that you're dealing with a vector. Let's hope that you get to see that all the time. That's one of the forms of vectors that you take. Another way that you can indicate a vector is in terms of unit vectors. Now let's see, unit vectors. Units are ones, so unit vectors would be one unit line. Unit vectors have a length of 1 and little I with an arrow over the top of it, which would be 1, 0, is a unit vector going to the right. So if you look at that, you can see it has an x component of 1 and a y component of 0, so it's going straight to the right, and it has a length of 1, and so it is a unit vector in that direction. So again, take care of the confusion. If you've dealt in your pre-calculus course with imaginary numbers, and you were looking at little I, well, that was a little different. And when you went and graphed it, you may have graphed the real part of the number horizontally and the imaginary part vertically. Not this case. I is going to the right. It's a unit vector in the x direction. And j, 0, 1. Nothing to the right or left. Up 1, length of 1 is a unit vector in the y direction, going vertically there. Okay? Since we add the x and y components of a vector together to get the actual resultant vector, we can express that vector we had before expressed as 2, 3. We can express that vector as 2i plus 3j. Means goes 2 unit vectors in the right, in the x direction, and then go 3 unit vectors in the vertical direction, and you'll get to where you want it to be. So 2, 3 is a vector, and 2i plus 3j are both exactly meaning the same thing. All right, more on adding vectors together. In component form, remember, like we did with our resolving of components in a triangle, that vectors that are in a straight line are simply added together. So 2 and minus 2 are both going to the horizontal, so you may add those together to get the result of that. 3 and 5 are both going vertically, so you may add those together and come up with a result there. So the resultant of adding these two vectors together, go 2 to the right and 2 to the left, that's a 0. Go 3 up and 5 more up, that's an 8. So we have 0, 8, or 8j, 0i plus 8j, if you want to put it that way. Here's a different example. Again, I'm adding the x components together. 2i plus 6i is 8i, and 3i plus negative 4j is negative 1j. Think of it, if you go 2 to the right and 6 more to the right, you are 8 to the right. If you go 3 up and then 4 down, your resultant is you are 1 unit down from where you were. So adding vectors together is pretty simple. I'm not going through a lot of example problems here, because your instructor can decide how much work on that you need. But we're just going to give you the basics here of what's going on with adding vectors together. Certainly subtracting vectors, like subtracting quantities, is adding the opposite. So if we were going to subtract the vector negative 2, 6, that would be the same as adding the opposite of negative 2, 6. Well, the opposite of going left 2 and up 6 is going right 2 and down 6. So the opposite of negative 2, 6 is 2, negative 6. then we can apply our addition rules and simply add those vectors together again. Okay? Not too difficult to do. 3 times v, you don't change the direction. 3 times v means you're going in the same direction, but you're going 3 times as long. So this is one example that we work out. So we're given vectors v and w here, as defined on the board that you can see here. So if we wanted 3 times v, we would take and go 3 times as far horizontally, 3 times as far vertically. So we would have 3v would be 6i plus 9j. If we had 2w, we'd go twice w minus 6i plus 12j. But since we are subtracting, we add the opposite of that. So we're adding positive 6i and negative 12j to come up with our resultant vector. If you need to stop it and slow this down and go through it slower, feel free to do that. All right, some more definitions. A position vector is a vector with the same length and direction as the given vector, but it starts at the origin. Now, when you get into polar coordinates, you're going to call that the pole, because it's where everything starts from. But it's the same thing. A vector with the same length and direction, but it starts at the origin. So here, let's do an example of this. Suppose we have a point P being 3, 4, and point Q is 5, 8. Now notice I didn't put a vector sign on those. Those are points that are there. So if you started at P, the vector PQ would go from 3 to 5, that's over 2 units, and would go up 4 units, from 4 to 8. So PQ could be represented by 2, 4. All right, so if we took another vector at the origin and went right 2 and up 4, that would be a position vector that represented the same thing. Now, what about the length of it? Well, the length isn't too hard to find. If you're going to the right 2 and up 4, Pythagorean theorem, square root of 2 squared plus 4 squared. The square root of 4 plus 16, which is the square root of 20, which simplifies to 2 radical 5. So that's, a little bit on length. You're going to be asked in problems, I'm sure, to find the length of some vectors that you're dealing with. Okay, last kind of part of this is the definition of a unit vector in the same direction. We know those unit vectors going straight to the right is I, going straight up is j. But what about if we want a vector that's only 1 unit long, but it doesn't go straight to the right or straight up, but it goes in the same direction as a given vector that we might have? All right, if a given vector was 6i plus 8j, you start out right now by verifying that the length of this vector is 10. Okay, supposedly I would think you drew a right triangle and went to the right 6 and up 8 and said, I recognize that one as the old 6, 8, 10 right triangle, so the length of that vector is 10. Now we want a vector that only has a unit of 1, which is 1/10 of that. So if we did this, if we took each dimension and just made it 1/10 as long as it was previously, we would have a vector that had a length of 1. You can certainly verify that. So our vector, our unit vector, would be 0.6, 0.8. If you do Pythagorean theorem on that, you will get 1.0 for the length of the vector, and it has the same relationship as the others did. The ratio between sides is still 6 to 8. So that's the position vector. The last concept that we're going to cover in the algebra of vectors is probably the one that is most useful to us after we get out of solving triangles and that sort of thing, but as far as algebraically goes, is called the dot product of two vectors. The dot product of two vectors is a single real number. It is not a vector. Before, if we added vectors together or subtracted them or did a scalar product, multiplied it by 3, we still had a vector when we got done. When we do the dot product of vectors, it is a single real number. All right? And it's real easy to find. If your vector A had coordinates x1, y1, and a second vector had coordinates x2, y2, then the dot product, and notice I used a dot symbol there, don't put a times sign there or a little dot, make something big so you can see it different, is a single number. You take x1 times x2 and add that to the result of taking y1 times y2. When you get done, you have a number. So let's see, here's an example. You work this one out right now and see what your dot product is. Okay, we're going to take 3 times 5 plus 4 times -2. We get 15 minus 8 equals 7. No problem if it comes out to be a negative number, it can do that. But, and you know, if your numbers you started with were somehow fractions, it could come out to be a fraction, but usually it's pretty easy to do. Our dot product here is 7. Well, okay, well, so great, the dot product is 7. What are we going to do with that? Well, here's what we're going to do with it. When we have that, the dot product comes into play when you want to calculate an angle between two non-zero vectors. Well, certainly if a vector is a zero vector, there's not much of an angle there. So we can apply the following formula. And the formula says the cosine of an angle between two vectors is equal to the dot product of the two vectors divided by the length of the first vector times the length of the second one. Okay? Now, of course, if we're finding the angle, there'd be an inverse involved. Here is the very last step. But when we look at it, you can find the angle if you simply know the coordinates of the vectors, or the IJ form. Find the length of each one, find the dot product, plug the numbers in, and do inverse cosine. So I want you to finish this sentence. Vectors A and B could only be perpendicular to each other if. Well, hopefully you figured out that the cosine of 90 degrees is 0, and the only way that you could have vectors that had an angle of 0 would be if the dot product of the two was 0, because the bottom of that fraction cannot be 0. They're non-zero vectors anyway. All right, so we're going to finish off here with a little contest between a couple of groups. All right? So here's what the contest looks like, a little speed thing to see who can come up with the angle between some vectors. Given two vectors A and B, you'll get those in a moment. You're going to find the angle between the vectors. All right, group 1, you're going to do it the old-fashioned way, without the dot product. You're first going to find the length of the vector C that connects the terminal points of A and B. Now you're not doing these head to tail, we're finding the angle between them. So they're both starting, A and B are starting from the same place. You're going to find the length of vector C, then you're going to use the law of cosines to determine the angle between A and B. You might want to, do this on some graph paper or something where you can do it fairly straight so you can see what's going on. So you can actually go over 2 and up 3, that sort of thing. So you might want to get ready now. So let's look at what group 1 is going to be doing. Okay? Group 1 is going to be taking, and let's say here's an example, vector 2, 4, and a vector -3, 5. So they're going to take and draw those two vectors on their thing. Remember, vector 2, 4 doesn't mean it has a certain thing, but it just goes, it happens. We're starting from the origin, so it does go to point 2, 4. -3, 5. We put them at the same point. So you're going to take, and of course you've got to find out the length of those, and of course you've got to take and somehow connect those two. Now when you connected them, you figured to go from point 2 to -3, you went 5 to the left, so that's -5. I could have drawn the vector the other way and it ended up as a +5. And to go from a height of 4 to a height of 5, it was going up 1. So there's your 3 vectors. So you can find the length of those using Pythagorean theorem. 2 squared plus 4 squared equals r squared for the first one. 3 squared plus 5 squared equals r squared for the second one. And 5 squared plus 1 squared equals r squared for the third one. So you can find those lengths and use the law of cosines to come up with the angle in between. So that length of the black one is a square root of 26. The length of vector A is 2 square root of 5, and vector B is square root of 34. So you can then use law of cosine since you have all 3 sides of that triangle, and you can come up with the final length. So go ahead and try that now. We're letting group 1 practice all you want to come up with that final length. Cosine C, angle C is 57.5 degrees. So there's your example. Now group 2, you would have simply found the length of those 2 vectors. You would have not needed the length of, you would have needed the length of this vector and the length of this one. You would have not needed the length of the third one and the dot product of those 2 things. So you would have still needed these numbers here. You would have still needed that length and that length for the bottom of your fraction, and you would have needed the dot product of those vectors for the top of your fraction. So, little contest to see whether it's useful to have the dot product or not. So on this last slide that we're going to see here, we're going to take and do the angle between these 2 vectors. So, here's the contest. Find the angle between them. Group 2, you know what you're going to do. We covered group 1 well. Here is the 2 vectors, 5, 2, and 2, 8. Try that now. We'll check it out for the final thing. Okay. Now, of course, as much as it's important to get speed into this thing, it's also important to get the right answer. 54.2 degrees is the correct answer for the angle between those 2 vectors. Okay, the last problem that we have to do in this section is probably, looks like it's going to be the most complex, but there's some real things you can learn from doing this problem that might not be done with a problem that sounds a little simpler. A proposed highway will have a bearing of south 15 degrees west. So all of a sudden you see we're listing the bearings in the second manner that we could do it from the town of Deadwood. The highway will cross an existing railroad track, the bearing of the track, and you get all sorts of information from here. So you can read through the rest of that for just a minute and we'll see what we can do with it. Okay, now as we look at this thing, we've kind of, I think, got to separate it out just a little bit. So let's start with just one piece of information that we see here. It says the proposed highway will have a bearing of south 15 degrees west from the town of Deadwood. So if we take a look at this thing for a minute, I've kind of indicated a little bit about the town and what we've got going on there. The bearing is taken from the town, and the normal direction is south and then 15 degrees west from there. So if we take this and look at this particular angle right here, that angle is 15 degrees. That little angle in there is 15 degrees. Let me just put a little arc in there so you can see it a little bit more. Right in there. 15 degrees. Now, I think the important thing that you're going to learn from this particular problem is how important it is to make a good drawing, and a lot of times to make separate drawings, because you try to put all these things in here. I've had students that I'll say, put in, draw the railroad track in. And I mean, we not only have tracks, but we've got the individual track parts and sections and everything else, and somebody probably put in a switching station somewhere. Don't make it too complicated. Try to take and separate things out a little bit and get it down. So I've got a single line for the track and a single point up there for the town. I drew in the axes so that you can see the difference there. I always look when I do any kind of axes and see, are there parallel lines? And by drawing in the axes, I can see where some of those angles are. That angle there becomes a 15-degree angle. Now, whether it's really important to me, I don't know yet. But I do know that by putting in a 15-degree angle here and here, I can start to see some of the things that might be important. Now, another piece of information that we had was that the bearing on the track was north 70 degrees east. So I'm going to take one more piece of information and put it in here. Don't try to look at every part at the same time. That's hard to do. Well, here's a bearing on the track of north 70 degrees east. So if we take the little part right there and look at that, we've got some of the angles put in. So I put a little bit of information in at one time. Now, I'm going to get some more information here. So going back to the problem a little bit here. It says from an arbitrary point on the track 2 miles from town, the town is at a bearing of north 30 degrees east. So I'm going to take my thing. I'm going to say, all right, let's see what else I've got here. An arbitrary bearing on the track 2 miles from town, north 30 degrees to the town. This angle here is a 30-degree angle, because that's the bearing of the town from a point on the track. Now that point on the track is 2 miles from town. I could put a 2 here at this time, so that's the one distance that I do know. But the important thing I want to get down is I want to get down, if that's a 30-degree angle, then this entire angle right here, all the way up there to that point, is also 30 degrees. Now that I'm starting to get some angles down, I can figure some things out a little bit. If I look backwards, that whole angle there is 30 degrees. If I go back here, I see that that part of the angle is 15 degrees. So if that little part of the angle is 15 degrees, and the entire angle is 30 degrees, then that means the angle inside the triangle there is also 15 degrees. So I'm going to go here and I'm going to label one of my angles here inside this triangle as 15 degrees. So I have a triangle now, and I know that we've got a 15-degree angle. Now if we go back a little bit again to the things that we knew that the bearing of the track, that entire angle that would be the bearing of the track, was 70 degrees. And in our second slide here, we knew that the angle from the axis over to the town was 30 degrees. That tells me that the remaining angle inside that triangle right here must be 40 degrees. So we can then put that information into our slide. But this is a 40-degree angle right here. And we now have a pretty easy problem to solve, actually, because we know two angles in the triangle. Because we know two angles in the triangle, we certainly can easily determine that this angle here is 125 degrees. And we have an angle of 125 and the side opposite that angle of 2. When we have that, we're kicking back to law of sines. The sine of 125 degrees over 2. Let's see which side we're trying to find. I've marked this with an X down here because we were supposed to figure out where this thing was crossing the track. We don't really care a lot about how far this is at this time. We wanted to know, how do we figure out where to put that little stake right here? Where we're going to put this little stake sitting right in that area there. So if we could find out the distance x, we'll know how far up the track to walk and make some markings there for where the highway is going to cross the track. So if we solve this, we know the angle opposite x is 15 degrees, so equals the sine of 15 degrees divided by length x. Back to your cross multiplication. I believe that if we both do our math correctly, we should get x is approximately 0.63 miles. So this problem wasn't a difficult problem, but the important things that we've learned in a lot of places is the real techniques that you need in life are not so much the solution to the problem, because sometimes problems don't solve out all that well. But being able to set up the problem is the key, because without that, you're not going to get a solution anyway. All right, that's the end of my part of the problems in this section. Your instructor will probably have a lot more things that he wants you to do here. I want to thank you for your attention to this stuff and all the other instructors that are presenting to you. I hope that you're getting a lot out of it. This ends my part of it. I will be around to visit your classrooms later this year. Thank you.